This is a video tutorial on how to use the chain rule to differentiate a composite function. A composite function is a function that has an outer function and an inner function, denoted here by f as the outer function and then g of x as the inner function. So in this situation, when you're trying to differentiate that function, you're going to use the chain rule. So the chain rule is given by this equation here. And what that states is the d dx, which is just our differentiation notation. To differentiate this composite function, you're first going to differentiate the outer function, denoted here by the prime, the f prime. You're going to leave the inner function alone, just g of x stays as g of x, and then this is in product with that inner function differentiated. So in the previous video, I go through how to use the chain rule on trigonometric functions, more simplistic functions than what you see here, mainly that the argument within them examples was just x. So over in the top right hand side, you can see that I've written down explicitly the differentiated values for these trigonometric functions. So d dx of sine goes to cosine, cosine x when differentiated goes to minus sine, tan when differentiated goes to sec squared, and then the exponential, the e to the x, stays the same. So e to the x differentiated is just e to the x. I briefly mentioned why. We know that d dxing these functions gives you the slope, the tangent value of any slope, and an exponential curve when that slope is taken at any point just equals 1. So that's why d dx e to the x is just e to the x. So first what we're going to do is we're going to apply this chain rule to these y equations. But to make it easier, instead of just going straight into it, what you should do is to draw the connection between the f function in the equation and in the chain rule, and the same with the g of x. Where is the g of x in the equation so you can directly see what's happening inside the chain rule? So the chain rule consists of two functions, as we mentioned, the f, which is the outer function, and the g of x, which is the inner. So the whole thing is just comprised of them two functions. So when we look at this y equation, the sine, the trigonometric entity here, that is the outer function. So this here is going to be your f of x function. So this is going to be the outer function. And then the 2 of x here, that's the g of x. So that's the inner function. So we have the sine as the outer function, and then we have the g of x is going to be the inner function. All right, so that in itself has, will just make it a lot more clear when now applying the chain rule. So let's apply the chain rule. So we want to differentiate this equation y. So we're going to have a dy dx. Right, this says, the chain rule says here, we have to differentiate the f of x first, the f value. So we know our f of x is sine. So the sine differentiated, we know from what we just were talking about over here, we know that that is cosine. We're also told that the g of x, so the argument, stays the same. So this g of x just stays as it is. Our g of x in this example is 2x, so we write down 2x as it doesn't change. And now we're told that this expression is in product with that inner function differentiated. So now what we have to do is we have to go back to this inner function and differentiate it. We know that 2x differentiated is just 2. So that's going to be cosine 2x by 2. And by convention, you bring the numeric part to the front as the coefficient. So that would just be 2 cosine 2 of x. So dy dx is 2 cosine 2x. That's the first example finished. All right, going on to the second example, we're going to do the exact same procedure. We're going to denote our outer function and our inner function, and then we're going to apply the chain rule and get the final dy dx value. So looking at this example, we can see that our outer function, which is our f function, we'll just write down as f of x, and we know the inner function here is our g of x. Now, once we have found our f of x and g of x, we then just have to basically execute this chain rule, follow these steps, and we have our result. Right, so let's write our final result. So dy dx. So the first thing we have to do, as we can see this is the chain rule, is we have to differentiate that outer function. So we have tan, so we have to differentiate tan. And again, from the top right hand side, we can see that tan differentiated is sec squared. So we write down sec squared. But remember, we're told that the argument, the g of x, stays the same. So this g of x stays as 2x cubed. Once again, that's this part of the chain rule complete, and we know that's in product with the inner function differentiated. Now we know how to differentiate these power expressions. We bring the 3 down as the coefficient, and that's in product with the 2, so that's going to give us a 6x, and we know the power reduces by 1, so that's x squared. Alright, so going on to example C, this is going to be a combination of, we're going to use a chain rule for the composite part of this equation, and then we're just going to use the power rule for the first expression in this equation. So if we want to differentiate x, we know that that's just going to be, so we have our dy dx, and we know that x differentiated is just 1, as the coefficient, or the power which is 1, comes down to the front, and then x to the power 0 occurs once you minus the 1, which gives us 1, and which then, when product with 1, will just give us 1. Okay, so we have 1 plus, now this is the composite function here, so this is our f of x, and then our g of x, so as similar to all these other examples over here. What is cosine differentiated? We can see up at the front that it's minus sine, so that's going to be minus sine, and we know that we're going to keep our g of x as it is at the moment, and then that's going to be in product with that g of x differentiated. So we know that 3x squared differentiated is going to be 6x. So tidying that up a little bit, we have our 1, and this is a minus sign, so we're going to have a minus here, and we're going to bring the 6x over as the coefficient. So it's going to be minus 6x sine 3x squared. Right, so this final example, I just moved it up here just to give us a little bit more room when going through it, as there's 1 or 2 extra points that I want to point out. The method doesn't change in essence. What we're doing is we're going to be differentiating function y, which is e to the power of this third order polynomial, 3x squared minus 4x cubed plus 7x plus 4. So nothing changes in that. We're going to denote our outer function, our inner function, and we're going to follow the same methodology as we did for all the other examples. The one thing that I'm going to change is that instead of rewriting this exponent each time, I'm just going to substitute a u of x in its place. So I'm just going to change this equation to e to the u of x. So u of x just being this polynomial here. It's just easier to deal with, but at the end, once we've actually applied the different operations that need be, we'll just substitute this expression back in for u, and all will be well. All right, so the first thing, as we did in the other examples, was define our outer function f and our inner function g of x. So in this example, our outer function, our f of x, is going to be the exponential here, and then our g of x is going to be the exponent here, which is our u of x, and in turn it's this polynomial here. So we have our f of x and we have our g of x, as we did in all the other examples, and now we're just going to apply the chain rule and get the final result. Alright, so to differentiate this y, firstly we of course have our dy dx. Now before actually applying the differentiation, I'm going to lay out what we will be differentiating, just so it's clear to you guys watching that we know what's going on. So the chain rule states that we differentiate the outer function, which is our e value, so essentially that's going to be d dx, and we're differentiating the outer, which is the e function, whereas the g of x stays the same. So our u of x is our g of x, that stays the same. So that's this part of the chain rule written out explicitly here, and then that's in product, but this time we're differentiating the inner function, the g of x, and we know our g of x is the u of x here. So that's going to be differentiate the u of x. Alright, so following then from this, we have to differentiate e to the u of x. But we know from over here that differentiating an exponential just gives us back that same exponential value. So if we want to differentiate e, that just gives us back the same, gives us back e u to the x. But now we know that's in product with the u of x, right? So now what we can do is if we substituted u of x substituted this polynomial back in for u of x, we're going to have, I'll just go one extra step just to be clear. We're going to ddx the 3x squared minus 4x cubed plus 7x plus 4. Okay, so that is then, the next step then is going to be, this stays the same, so e of u of x, we've already differentiated that, and that's in product with ddx of this u of x value. So how do we differentiate the first expression? We're just going to use the power rule. So that's, the 2 is going to come down as a coefficient, so then that's going to be 6x. Differentiating the next expression, that's going to be a minus 12x squared, and this 7x is going to turn to plus 7, and then the constant goes to 0 as we're aware. Alright, so now our differentiation has turned into e to the u of x multiplied by the inner function differentiated. So now I can insert our u of x back in here to give us our final result. So the final result is going to be dy dx. Well, e to the u of x, we know that u of x is this exponent here, so that's just going to be our 3x squared minus 4x cubed plus 7x plus 4. So that's our e of u of x filled in, and we know that then is just in product with this expression here, so that's going to be 6x minus 12x squared plus 7. So I hope you enjoyed it. A like and subscription would be great, much appreciated, and see you in the next video.